See, RLC in parallel and we have applied the current source, whereas in series we had RLC in series and we had applied the voltage source, which is AC. Understand? Now we say that this parallel resonance is the dual of this series resonance circuits. What does that mean? Right? It means that in series resonance, if you are dealing with Z, in parallel resonance you'll be dealing with 1 by Z, that is admittance. If you deal with impedance in series resonant, then in parallel resonant you'll be dealing with admittance. If you're dealing with R, you'll be substituting that R with 1 by R, C by L and L by C. This is what is the meaning of dual. Understand? So since we have to be looking at the admittance, this is how the admittance looks like. See here, 1 by R plus J into the susceptance. I just discussed all this yesterday. Fine. See here, if this is the impedance of the series resonant circuit, the admittance of the parallel resonant circuit is given by this. Why? Because Z has to be replaced by 1 by Z and 1 by Z is admittance. Y. R has to be replaced by 1 by R. If R is the resistance, 1 by R is called as the conductance. Okay. Omega L would become omega C because L has to be replaced by C, and 1 by omega C would become 1 by omega L because C has to be replaced by L. So if this is reactance of the series resonant circuit, fine, this is the susceptance. So conductance plus susceptance will give you admittance, whereas resistance plus reactance will give you impedance. This is for series resonance. Okay, so following the duality, if you obtain the equation here, this would become the admittance of the parallel resonating circuit. Okay, and we also saw these conditions at resonance. What was happening at resonance? This reactance is 0, right? We can say reactance is 0, or you can also say the reactance of inductance is equal to the reactance of the capacitance. Okay, since these two are equal, these two get cancelled and you will left with Z equal to R. This is what is happening in at resonance. Okay, similarly if you follow duality, so this is what is happening. C is replaced by L and L is replaced by uh, C. Okay, and R has to be replaced by 1 by R and Z has to be replaced by 1 by Z. That is what is done here. Fine. Now also at half power frequencies we saw that the reactance is equal to the resistance. Here what would happen? The susceptance would become equal to the conductance. This is called as conductance, this is called as susceptance. This is reactance and resistance. This is susceptance and conductance, the inverse of the resistance. Fine. And we also saw the other equations also. We saw the equations for omega 1, omega 2. Okay, and once we know what is omega and omega 2, it would be easier to get our bandwidth. Fine. So these are the equations that we have seen. So just you have to replace the proper terms here. Fine, you will get the same equations for parallel resonance. And one more thing that we discussed yesterday was the plot of I versus F that we used to do in series resonance. Okay, so you plot I for varying F. Here you will be plotting V for varying F. The rest, everything would remain the same. It's almost the same. Okay, even I would go to maximum at F0. Here also we would go to maximum at F0. Fine. As at F1 and F2, the value of current is I naught by root 2. Here also at F1 and F2, the value of V would be V naught by root 2. There's absolutely no difference there as far as the response is concerned. But what is being seen as the frequency is varied is what we need to be a little careful about. Fine. And since here this is quality factor. See again the duality is maintained. Omega naught is retained as it is. L is replaced by C and 1 by R. Here R is replaced by 1 by R, so that would come in the numerator. So the same thing is repeating. So whichever the equations you have seen in series resonance, okay, if you know that, if you remember that, bringing that for the parallel resonance circuit is not at all difficult. So that is what we had discussed earlier. Now we also saw how to obtain the resonant frequency for parallel resonance circuit. Okay, so there in series resonance we started by considering the impedance of the circuit, whereas here we are starting by considering the admittance of the circuit. Fine. So this is the admittance, this is the conductance, this is the susceptance. And what happens at resonance? as we have seen earlier, there the reactance was getting 0. Here the susceptance would get 0. Since susceptance is getting 0 at resonance, we can set omega equal to omega 2. Okay, this part would be 0. And once this part is 0, what would happen at resonance? This admittance would be equal to the conductance at resonance. But what is that we need to look at? We need to look at the resonant frequency. That's why we considered equation number 2. Okay, and very similar to what happened in series resonance, also here also omega naught is happening to 1 by root LC. Okay, and which means that F naught is 1 by 2 pi root LC. Understand that? Here it's again it's following the duality. See, we replace L by C, C by L, nothing happens. Okay, it remains the same. That's why the same frequency comes there. The equation for resonance at for resonant frequency, the equation is same in series resonance as well as parallel resonance. Okay, so this is what we had seen earlier. Today we shall see another derivation wherein we are deriving the equations for omega 1 and omega 2. Okay, take them that as your heading. Those, yeah, you can go on with this. What we're doing today, let's make some more space. Yeah, equations for everybody take down this. Equations for omega 2 and omega 1. Also the bandwidth. Since omega 1 and omega 2 we are obtaining the bandwidth would not be difficult. Okay, so we are doing this. So how do we start? We need to look at the response. I've already told you how the response looks like. Okay, let's take the x-axis and y-axis. Let's draw that. Fine. Now, very similar to what was happening earlier, here we are varying the frequency. Here we were dealing with I in series resonance, we'll be dealing with V. Okay, the response would not change, response would remain the same rather. At this point, what is this? The maximum value of V is V naught. When are we getting that? At resonance we are getting that. So this is resonant frequency. Fine. So here you have F1 and F2, or you can also say this is omega 1, this is okay, this is omega naught and this is omega 2. You should take this as the frequency in radians per second. It's all the same. So what is your voltage at the half power points? It is V naught by root 2. You can call them as V naught by root 2, or you can also say this is 0.707 times V naught. Okay, whichever the way you want to look at it. It's fine. So we are interested in getting the equations for omega 2 and omega 1. What is the bandwidth? This is the bandwidth. What is bandwidth given by? Bandwidth is, this is the bandwidth. What is it given? It is given by omega 2 minus omega 1. Understand that? So let's move on with the derivation. Fine. Now, since we are dealing with voltage, let's write the equation for voltage. Anybody who wants to give me the equation for voltage? V. How do we used to write I? I we used to write as in series we used to write I as V by Z. Okay, since we are not dealing with Z, we are dealing with Y. I can say it's V Y. So what would be our V? Why are we dealing with Y? Because it's parallel resonance. Okay, since we are dealing with Y, our V would be equal to I by Y. Everybody understand that? So V is given by the current, okay, divided by the admittance Y. Right? Call this as equation number 1. Similarly, at half power frequencies, what's happening? At half power frequency, what is V? What is V? V is V naught by root 2. What is V naught? V naught is the maximum voltage. It's I into, what is V? V is equal to I by Y, right? And we know that V is I by Y, but here see, V is equal to I by Y, but Y is equal to what? 1 by R at omega equal to omega what? Omega naught, or that at when it is maximum. When would this be V naught is the maximum voltage, right? So V is equal to IR, but yeah, so this is what we need to write. How we have got this, you should understand. Okay, V is equal to IR. Why we are not dealing with admittance here? Because we are dealing with voltage, we are dealing with the parallel resonance circuit. So V naught is I into R, your Ohm's law. Okay, divided by root 2. V is equal to IR divided by root 2. So from one end to what we can do? From equations 1 and 2, I by Y, I divided by Y is actually equal to IR by root 2. Okay, here I and I goes off. So you're left with what? You're left with 1 by Y equal to so this implies that our 1 by Y is equal to R by root 2. Now what is Y given by? We know that Y is 1 by R plus J square root of omega C minus 1 by omega L. Okay, what is magnitude Y? Magnitude Y is square root of what? 1 by R square, okay, plus what? So what happened here? Something wrong? Square root of this square root is not there, right? The square root would rather come in. Sorry, yeah. The square root is not here. It is just this. Okay. When we come to this, we'll have square root of a square plus b square form with magnitude. Fine. So therefore, we can say 1 by square root of 1 by R squared plus omega C minus 1 by omega L squared would be equal to R by root 2. Now this square root would again pose the problem. So what we should be doing for that, to get rid of the square root, we need to just square the whole equation. So squaring both sides, what we get? Yeah, squaring both sides, we get this. I hope you're all making note of this. Squaring both sides will be left with 1 by r squared plus omega c minus 1 by omega l whole squared equal to r squared by root 2. R square root 2 would go off, so we just left with 2 there. Okay, because we are squaring. Now what would happen? This implies that, so this particular equation implies that 1 by r squared plus omega c minus 1 by omega l whole squared, which is taking the inverse of this, will become 2 by r squared. Understand that? Now what happens? This is also 1 by squared. You can write this as 1 by squared if you want. That would make it. Let's have this as 1 by r squared. So you have 1 by r squared here, and here you have 2 times 1 by r squared. So what would happen? This implies that or omega c minus 1 by omega l would be equal to, so square, and let's take this square here. What would this be equal? This would be equal to 1 by r square. So taking the square roots on both the sides, what would we get is this. Yeah. So what would we get? Square root simplify. Both sides. What would that imply? It would imply omega c minus 1 by omega l would be equal to plus or minus 1 by r. What's happening now? This is very important condition. This is not what we are taking, but this is very important condition. What is it saying? At half power points, our susceptance is equal to the conductance of the circuit, of the parallel resonant circuit. Therefore, at omega 1 and omega 2, the susceptance is equal to conductance. Okay, in parallel resonant circuit, parallel RLC circuit. So this is something that one should understand. Now, what is the purpose here? The purpose is to find out omega 1 and omega 2. Fine. So let's call this as so at omega 1, what's happening? Therefore, at omega equal to omega 2, what would happen? That equation would become omega 2c minus 1 by omega 2l equal to plus 1 by r. Take the LCM and obtain the quadratic equation and find the solution for the quadratic equation. Understand that? So how would that become? So this would become, this implies that we have omega 2 square LC minus 1 equal to omega 2 L by taking the LCM and taking denominator onto the right hand side. I have done. Fine. So further, how does it look like? It looks like, further it looks like omega 2 squared RLC minus R, or minus R we can keep later on, okay, because we want the quadratic equation. Let's put the quadratic equation in proper order, okay. So minus omega 2 L minus R would be equal to 0. Fine. So using that standard equation for the roots of the quadratic equation, we can write that therefore our omega 2 would be equal to what? L, okay, then plus, they say plus or minus, so let's take just plus square root of L square plus 4AC, right? 4 A is LCR, RLC, C is again R, so let's write R square divided by 2A, they say, right? What is A? A is RLC, so it is 2RLC. Fine. So therefore, omega 2 would be what? Omega 2 would be 1 by 2 RC plus square root of what? What would it become? Plus square root of 1 by 2 RC square. So this denominator is being taken into the square root and a square is being attached. Okay, that is, this is being squared. The denominator is being squared so that it can be taken inside the square root. Understand? Plus 1 by L C. Understand that? So this is what is your omega 2. Everybody is okay with this? This is very similar to the omega 1 and omega 2 that we have obtained for series RLC circuit. Okay, so let's put this in a box, and similarly you can obtain the equation for omega 1 also. Okay, so similarly let's write that. Let's not do it. Let's just say similarly our omega 1 is minus 1 by 2 RC plus square root of 1 by 2 RC squared plus 1 by LC. Fine. These two equations were asked to be derived. So we have derived the equations for omega 1 and omega 2 of the parallel RLC circuit. Get this? Now, once we have omega 1 and omega 2, obtaining bandwidth would not be a problem. Okay, so what is bandwidth given by? As we have seen, the bandwidth is given by here omega 2 minus omega 1. Fine. So if you subtract omega 1 from omega 2, okay, if you subtract omega 1 from omega 2, what you would get is 1 by RC. So you remember the equation for R by L, right? We had omega 2 minus omega 1 for series resonant circuit as R by L. So R is replaced by 1 by R, okay, and C is replaced by L. So this is the duality would be there always in all the equations, okay. Since our omega 2 minus omega 1 is R1 by RC, it implies that R F2 minus F1 would be equal to 1 by 2 pi, okay, RC. This is your bandwidth. So this is our bandwidth in hertz. Right? This is bandwidth in omega 2 and omega 1 is bandwidth in radians per second. Get that point? So this is how we can obtain the equation for bandwidth. Now, let's take another circuit. Now the circuit that we have seen so far, okay, the circuit that we have seen so far is a theoretical circuit. Actually, if we have to use parallel resonance circuit, we don't use this parallel RLC circuit as it is, as we have seen in this case. That's not practical circuit. Practically, there is a circuit which is used in the applications. Okay, so that we shall see now. Fine. Now take the heading as practical parallel resonant circuit. Practical parallel resonant circuit. New subpage. Yeah, take the heading as practical parallel. Why we are doing this? Because the parallel RLC circuit that we discussed just now is theoretical. Okay, so now we shall see the practical parallel resonant circuit. Fine. How does it look like? Everybody just copy down the circuit. Maybe we shall take in the next class if the time does not allow us. Time allows, maybe we have 10 more minutes. I think we can deal with the initial part of this. Everybody take down the circuit. It is the practical circuit that we are taking. What's happening here? You have R and you have L in one branch. Okay. In another branch, you have your C. Fine. Now across this, we apply the voltage. Okay, which is AC plus minus and a current flows here. Fine. So this is referred to as the resistance R, inductor L, and this is C. Fine. Now this, when this current comes here, it gets divided into two parts. One part would come here, okay, and that is called as the current which is flowing in the branch where L is connected, and this is another part of that current which will flow in the branch where the C, the capacitor, is connected. Understand this? The circuit that we have seen previously is not practical one. So that is helpful just to understand that the duality is maintained when we consider that theoretical parallel resonance circuits, wherein all the components R, L, C comes in parallel. But in practical parallel resonance circuit, you can see that R and L would come in series and the C would come in the parallel with this particular branch. Now you can ask me, why R and L only in series? Why not C in series and L here? Understand, if any conducting wire you take, any conducting wire, or you can say any conductor length, a length of the conductor you take, you should understand that if we bring them into wind, if we wind them, if I get the winding like this, you see this, there is winding. This is inductor which has got windings. Okay, so when you wind that conducting wire, what happens is there will be the resistance of this winding. Okay, and that resistance of the winding would always come in series with the inductor. So if you have a resistance would not be in series with capacitance. Resistance would always be in the series with the inductor. Understand that? That's why you should understand. Okay, our resistance should always be connected in series with the inductor, right? Not the capacitor. Okay with that? And C would come in parallel with that branch. And mind you, what we are applying here is voltage only. You may see here in parallel resonance circuit, okay, we did this. We took this as RLC, right? And we applied current. So this is to understand the duality. We said that the parallel circuit is dual of the series circuit, series RLC circuit. So to demonstrate that, we took this circuit, but this is not a practical circuit. Understand that this is more helpful in understanding theoretical concepts of duality. Understand, but practically this is what is used. Fine. Now what we need to do for this circuit is to obtain the condition for resonance. So when do you think this circuit would resonate? When do you think the series circuit would resonate? The series circuit would resonate at f naught equal to 1 by 2 pi root LC. Similarly, the theoretical parallel resonance circuit would also resonate at f naught equal to 1 by 2 pi root LC. But would it be the same for the practical parallel resonance circuit is something that we can look into by finding out the condition for resonance. Okay, so take the heading as condition for resonance. So they're all very popular questions in the exam. Fine, obtain the conditions for practical parallel resonance circuit, they'll say. So what is that condition for practical parallel resonance? We are obtaining the frequency at which this circuit would resonate. Okay, so it means to say obtain the frequency at which the circuit resonates. This is the meaning of it. We are obtaining the condition for parallel condition for resonance means we are obtaining the equation for the frequency at which the circuit would resonate. Everybody understand that? Okay, so we shall take this particular condition for resonance in the coming class. Okay, on Monday.